Welcome to this NPTEL course on principles and techniques of modern radar systems. So, in previous lecture we have seen CW radar, continuous wave radar. Now, today we will see a variation of that CW radar called FMCW radar. Now, we discussed that CW radar cannot measure range, because if you say send a signal continuously, then there is no timing mark on the signal that when it is starting, and so when the echo is received, that it is with respect to which signal transmitted, that is not known. More specifically, that I do not have a mark for time of transmission, I do not have a mark for time of reception. So, transit time we cannot measure, and we know that the radar range is measured by measuring this transit time. So, if we cannot accurately measure this transit time, the measurement of range we cannot do. Now, actually if we look at the frequency domain, a CW radar, that means it is operating at a continuous fixed frequency. So, the its Fourier in the frequency domain, it will be a single function. So, there is no distinct mark there, no sharp timing mark. Now, so if I want to measure put that mark, I can broaden the spectrum. So, one way of broadening it, we know that modulation, which communication people use for transmitting signal. Now, modulation can broaden the spectrum of a signal. So, if we do that here, though we are not sending it for communication purposes, but that can serve our purpose. That type of radar is called FMCW radar, frequency modulated CW radar. We know frequency modulation changes the spectrum, it gives a broad spectrum. So, you see this is one application of modulation, frequency modulation for measurement, that we want to do range measurement for that modulation. Now, if we do amplitude modulation, actually that is the pulse radar, because I have a RF signal. Now, you see that if I put that this is my amplitude modulation. So, this on and off, this is basically nothing but pulsed radar. We will see that later. We have understood various basic parameters of radar with the help of pulse radar. Pulse radar waveform is something like this. Whereas, if I do the same thing in frequency, so you see that I am changing the frequency. This is actually the FM CW radar. So, the timing mark here, as we will see, that is obtained because I am changing the frequency of the signal in a predetermined fashion. So, that will put the mark. Also, we will see that instead of sending one pulse, if I send, suppose this is one frequency, if I send another frequency signal, this also puts a mark, because in the frequency domain they will be given by two delta functions. So, that also is a broadening of the spectrum, that also can give that mark. So, these are the two varieties of range modifying the CW radar for doing measurement. The first variety is called FMCW, the second one is called double frequency CW. Both we will discuss. First, we will discuss the FMCW. So, with time I am changing the frequency in FMCW. Now, more is my frequency deviation, that means given an unit time, the more I can change the frequency, more will be the broadening of the spectrum and more will be my accuracy in the measurement. So, it is better that if I can do more frequency deviation in the frequency modulation, but obviously you know that there is a limitation because my electronics should support that. So, I cannot go on doing that indefinitely. Within the practical limit I will have to do this. Now, let us start the thing with a diagram. Actually, in FMCW the frequency is changed with time. First we assume that it is being done in a linear fashion, though later we will see that other fashions, other things are possible. So, what I am doing? I am plotting the time versus frequency of the transmitted signal. Transmitted signal. So, this is the plot of transmitted signal. So, let us say that at initial time the frequency is f naught and then I let us say change it in a linear fashion. So, I can say that this is the transmitted signal. So, its frequency is changing linearly with time. Now, let me put. So, obviously, after some time I will get the echo signal because echo will take some time to come. So, the echo signal will be something like this and this I am calling the echo signal. And you see that suppose at a particular time, suppose this is the time I am interested doing the measurement that echo has come. So, that time already from the signal with which the echo has been signal has been transmitted, compared to that it has changed because echo was sent a bit before. So, maybe somewhere here the transmitted signal was, but due to the transit time. So, what is the transit time at any frequency? If I draw a curve, this is actually my transit time. So, I can say this is my delta t and this is echo signal. So, you see that at any time if I see between that time what is being transmitted and what has been received, there is a frequency change. So, that means if I mix the transmitted signal at this time with the received signal at this time, at this instant, then there will be a bit frequency created. Now, here I am assuming that the target is stationary. So, this bit frequency is not due to the motion of the target. I am first doing that, later I will remove this restriction. So, even if the target is stationary, that means it is not creating any Doppler because there is no relative motion now. But just because my modulation, just because I am changing the frequency of the transmitted signal. So, when I receive that, there will be a difference in frequency, usually this. So, this frequency, if it is small, it will produce a bit. So, that we call bit frequency. So, this bit frequency will depend on what? Will depend on this delta t. And what is delta t? Delta t is proportional to the range. The more distance the target is, the more delta t is there, that we have seen that delta t is equal to 2 r by c. So, that means if now this f b, that is a function of delta t, linear function of delta t, and that it is also a function of range. So, basically by measuring this bit frequency, I will be able to tell what is the range. So, this is the principle of FMCW radar. So, I can say that delta t is 2r by c, this we know, and so whatever received signal I am getting, the echo, I am heterodyning that with a portion of the transmitted signal. So, I am taking always the transmitted signal. So, these two I am mixing, I get a bit frequency FD. So, this bit frequency is a, I can say FB is a measure of range. Now, if the target is moving, then also there will be a beat, because due to this there will be a difference, also there will be a Doppler shift. So, these two will superimpose. So, that is also beat frequency. So, to distinguish these two cases, that due to range there is a beat. So, I will say that beat is due to two things, due to A, the range of the target, and B is due to the velocity of the target. So, I will first distinguish that is why actually you see target I have initially assumed stationary. So, that I am getting the due to range what is the beat. So, this only for range, that we will be calling FR, that frequency. So, beat frequency when only range is present, only due to range, that is FR. Beat frequency only due to velocity, that will be calling FD, F Doppler. So, in actual cases it will be mixture of the two. Now, I can first derive an expression for FR only due to range. So, I can say that FR is equal to FB when target stationary and can I say that I know how I am changing the frequency, because if I look at that graph, that I know the fashion I am doing. So, I can say that in delta t time how much I have changed. So, there is a slope of this graph, that multiplied by delta t will be the delta f. So, I can write from these that what is delta f? The change in frequency, that is nothing but df dt into delta t, or I can say f dot into delta t. Okay. So, this I know, because what is the slope of this graph, how my electronics is changing, that I know, that in what way I am varying. So, f dashed is known, delta t I am measuring, and so I will be able to tell. So, now I will write that FR is equal to FB. Now, what is FR? FR is F dot into delta t. Now, that is F dot. What is delta t? 2R by C. So, if we now we will have to specify F dot. So, for that what I will do? I will do another graph that. So, again I am doing that. I have a transmitted frequency. Now, in any practical circuitry, you see I cannot go on increasing the frequency. So, I will have to come down, because after a maximum frequency more cannot be, an oscillator cannot go on changing its frequency indefinitely higher and higher. So, I will have to come down. So, I will have something like this. So, this is my T, this is my F. So, this is my transmitted signal, and the echo signal I will get after some time. So, that will go, then that will also come down, that will come down, and then that will go. Okay. So, here I can say that what is the rate or what is the time period of change of the frequency. So, I am starting from here. So, this is the full period. So, I can say that modulation period, that I can call, because here it is going up. So, again another point where it is going up. So, this I will. So, there is a modulation frequency. So, this is 1 by that. So, if modulation frequency is FM, then I can say that this time period is 1 by FM. Okay. So, this, and here I know that at what is delta F. So, maximum what I am changing, you see that this, and this is the minimum. So, I can say that this is my total delta F. So, what is my F dashed, the df dt, that I can say this delta F, the total, divided by 1 by Fm. So, I will write that what is my F dot is this delta F by 1 by Fm. So, now you see that if I plot the beat frequency in this same graph in time, what I will get, this is one point, you see that I mark this when the transmitted signal frequency and received signal frequency, they are meeting. Similarly, again they are meeting here, you see that this one, then again that meeting is not here. So, if I plot this graph in some other color, so I can plot the beat frequency due to range, or you can say FB, or that is at present that is FR. So, how that will you see here everywhere the difference at any point, these two are parallel graphs. So, here only where it is not parallel, when it has started coming down. So, from that time, but that means I will get something like this, then at from this point where the transmitted frequency is coming down, the difference between the two is coming down, and at this point it will touch 0. So, it will be something like this is the beat frequency, then again it will go up, and then again it will go up to where again when this maximum minimum is there. So, that time again it will come down like that. So, this is the beat frequency curve. So, you see that here only this is not constant, but here it is a constant. So, I can measure it, and from that I will be able to find out. So, this is called turnaround region, except turnaround region the beat frequency is constant. So, and the beat frequency goes to 0, no beat, when the transmitted signal frequency graph touches the received echo frequency graph. So, now I know a dot, because this is the property of the modulator, which is in our hand. So, we can write from here that what is the FR expression. So, f r is, we have derived till here that f dot into 2 r by c, here we left. Now, I will just put the value of f dash. So, if I do that, that means f dot is delta f is the total change in frequency by 1 by f m is the modulating frequency into 2 r by c. So, from this I can find out that what is the range. R is f r, what I observed, into c by 4 f m delta f. So, this is a very useful relation, that what is the range of the stationary target. So, the bit frequency observed f r, c I know velocity of light, then f m is the modulating frequency and the delta f is the total change in the frequency. So, now with this I say that actually there is a, let us say there is a Doppler. So, no more I am assuming stationary target, now I assume a moving target. So, what will happen? There will be a Doppler. Now, that Doppler may be positive, may be negative, because depending on whether I have a closing target or a receiving target. If I have a closing target, there will be a positive Doppler. If I have a receding target, there will be a negative Doppler. So, that means this curve, that means the received curve, this blue one, that will shift up and down, but no shift in time axis. So, depending on the target closing or receding, the curve goes up, signal frequency curve, received signal frequency curve goes up or down with respect to the transmitted signal. So, let us say that if I have a, that won't be a good color, I have taken that, let me take this. So, what will be the this curve? This curve will be something like this. This is the, if I have a closing target. So, in time it will have to come same. So, that means this curve will cross this early, will cross this curve and go somewhere here and then come. So, you see that what is this difference? So, from here to here, this difference is our Doppler f, I think small d. So, this, and in the same graph down, if I put this a thing. So, you see the, if the curve goes up, so the bit frequency will change. So, now I will plot with this, the I will say FB curve, general bit frequency. So, it will be down. So, it will be constant here, and it will, in the time axis there is no change. So, it will go like this, and in the other half you see, if you see this curve, that compared to the transmitted, here the difference is less, but in the second half, that means in the next half cycle, the difference is much more. So, the bit frequency will increase. So, this curve will go something like here, this, again from here it will go down, then again here this is it. So, you see in one half cycle, the when the moving target is there. So, the curve is below the constant target curve, and in another half cycle it is above the constant half cycle curve. So, what is the effect of Doppler shift? Doppler shift has the increase the bit frequency in one half cycle, in the other half cycle of the modulating period it has decreased. So, that now we will have to mathematically express. So, suppose for a moving target we know that it can be either closing or a. So, let us assume that target is closing. So, if the target is closing, also you see the range is producing a frequency change, and also the Doppler is producing the frequency. And now, range and velocity, now how much frequency change they are produced, there can be two cases again. So, if after target is closing, we also have two cases, whether Fr is greater than Fd or Fr is less than Fd. There are two cases. Now, usually in radars, if the generally range is more and the velocity, so generally Fr is greater than Fd, but obviously if it comes very near, then this condition also can come. So, first we are assuming target is closing as well as and Fr is greater than Fd. So, that graph we have already drawn. So, we can say that, let us say that in the half cycle the first half cycle, this is, you see the total period is 1 by Fm. So, this is 1 by 2 Fm. So, this is we are calling up portion of the cycle, and because here the curve is up than the stationary, and this is the down cycle. With this terminology, I can say that what is Fb up? Fb up will be Fr minus Fd, and what is Fb down? That is Fr plus Fd. Now, can I do both the velocity and range measurement? That means, if I can find out Fr and if I can find out Fd separately, then I can find both the velocity and the range. So, that can be easily done. You see that if I sum these two, then I can, then Fd will cancel, and Fr is nothing but half of Fb up plus Fb down. Now, Fb up and Fb down can be measured, because I know the modulation cycles. So, in the first cycle I will put a counter on and that measurement of Fb, that I will call Fb up. Similarly, I can measure Fb down, I will sum them, I will get Fr. If I take the difference between Fb down and Fbr, then you see that half Fb down minus Fb up. So, on the other hand, if I have this condition, that this is a high speed target at short range, in that case, so this averaging meter, if you do this, then the averaging meter, so that means this is the averaging meter, that will be giving you Fd. So, Fd is the half of Fb up plus Fb down in this case, and this is the averaging meter, and the difference meter, that will give you the range. So, half FB up minus FB down. You see the signs will change, that is why I have taken that. So, to understand that, because I will have from these two measurement there will be an averaging meter, there will be a difference meter. Now, what it is giving, to know that we need to have an a priori idea that what is these conditions. So, this information is required, then only we will be able to correctly interpret, and generally that is known, because you know that already once you do the range measurement, and if you follow, you can find out whether it is the case, because ranges are generally measured before. So, this knowledge if it is has, it can correctly find out this. Now, one question is that modulation of the frequency, do we have to make it always linear, because that means I will have to have a ramp, then it should come down. So, that can we not have any other type of, particularly like our communication thing, can we have a sinusoidal variation? That means, if my variation is frequency is varying like this, then obviously the beat frequency won't be constant there over even for a half cycle, but we will show in the next lecture that that also is possible. Only thing is, if you have a multiple target detection problem by the FMCW radar, then it is necessary to have linear modulation, because each target should have a corresponding beat frequency. But if you are trying to detect a single target, actually FMCW radars, you see they are not used for mainly detection of the distant aircrafts or naval ships, etc. They are used, as I said, in low range cases where suppose the altimeter, that means height of the aircraft is measured by that, etc. Radar altimeter, where ground is your target. So, in that, if you have want to have that linear modulation like ramp type, then the cost increases, complexity increases. So, sinusoidal modulation is better, but I know that the beat frequency won't be changing, because sinusoidal modulation means your transmitter frequency that is changing with what I have drawn, that continuously it is going increasing. I am not doing that in a hurry. So, that beat frequency won't be constant over a half cycle, but we will show that by averaging you can find out the range. That will be our discussion in the next class, because FMCW is mainly used for these short ranges. They are, if we can make the electronics or transmitter design simpler, that will be better. So, that we will take up next. Thank you.